Hi, I'm Marc Charlebois, Director of Engineering in the Machine Learning Group at Qualcomm. So today I want to go through a deep dive of Qualcomm's AI software, actually more accurately the deep learning software, and talk about some of the solutions we have, give you an architectural overview, and look at how some of them have been used even by some third parties. But at first I want to start and give a sort of high-level overall context. We've heard today in the keynotes this morning from Chris about the last decade has been mobile first, and the next decade is going to be about AI first. But really, the mobile that you have, your devices, is going to be the nexus of both those things. It's going to still be your view to the world and the thing that you always have with you, and a really central nexus of AI innovation. In the next 4 years, there's going to be 8.6 billion mobile phones shipped. And if you look, that's currently the population of the Earth, at least as of 7:20 this morning, on the World Population Calculator. So the kinds of experiences we're seeing from AI, for camera, for voice recognition, for keyword recognition, is really providing a whole bunch of new experiences for people. And I think you can see this every day as new features come to phones. It seems to be for everyone pretty much, except unfortunately Andrea, who seems impervious to voice recognition. So I'll give you a brief history of the evolution of what we've been doing for AI on Snapdragon. So we started out supporting cafe models, and for some reason, there we are. And these were taking the proto-text files and basically converting them to our own custom runtime, running them on the CPU, doing things like face recognition. And that was done back in 2015 on the Snapdragon 820 chip. The training would be done in the cloud or on a server, then deployed to the device using the converted cafe models that would then run on the runtime. So in the next 2016, 2017, we did a lot of support for additional networks, for TensorFlow, for Cafe2, creating new converters that would be able to take those protobuf formats and convert them to our runtimes, to a new format that we call a DLC, which was a deep learning container. And so these would obviously have to have separate converters for each of them. We could go through a quantization phase that would then be allowed to support the DSP, which runs quantized networks. You can see the overall architecture where we have the Qualcomm Neural Processing SDK, which supports running networks across the CPU, the GPU, and the DSP. We have something called QSML, which supports accelerated operations. It's like a BLAST library. It supports those kinds of acceleration, especially using Neon. The GPU ops, which are basically OpenCL kernels that run on the Adreno GPU. And then DSP operations, which are leveraging the open source Hexagon NN neural process, basically set of operations that are available for accelerating machine learning operations on the DSP. And it's using a newer hardware technology we have called HVX. There we go. So now you can see in 2018 the growth of the support of all of these different networks. And a lot of this has come from the ability of these networks to convert their models through ONNX. And we now have an ONNX converter that allows us to import all those models that are generated from different frameworks and run them on the runtime. So you see the DLC model loader takes in those networks that have been converted through the converter, or we have the option potentially through the Android NN runtime that is also supported through the Android BSPs to take in TensorFlow models and run them directly through the Android NN interface. And again, this would be, so this is support as of this year, was deployed out on the Snapdragon 845 models. So So the whole combination of these things we call the AI engine. And that's the combination of support for the DSP, the GPU, the CPU, using Qualcomm's neural processing SDK, supported via Android NN on Android platforms, and then using the Hexagon NN library as well. Supporting networks that were designed by Caffe, Caffe2, TensorFlow or TensorFlow Lite, or anything that can be imported through Onyx. Here's a diagram of the software stack in general. So we have mobile applications that can be written using a variety of approaches. It's possible to write things that go directly to either Vulkan or OpenGLES or use RenderScript. You can write something that directly interfaces with OpenCL on the platform. Or if you're going through Android NN API, you can target through the GPU backend using OpenCL. You go through Android NN, again, the same way, but targeting the DSP with the Hexagon NN backend. And then if you're using the neural processing engine, excuse me, some more. Through the DLC, you can run things on the CPU, the GPU, or the DSP as well. If you're using TensorFlow models, the TF Lite runtime can run directly on the CPU here, or there's other frameworks. And in fact, I gave some patches to the T-Engine project that allow it to run on the 820. And so that would go directly through using the CPU backend, accelerated by Neon. So the SDK also comes with a bunch of tutorial samples, benchmarking, user reference docs, and debug tools. And I'll get into more of the tools that come in the SDK in a sec. All right, so you can download the Hexagon, not the Hexagon one. I'll get to that a little later in the presentation. The Qualcomm Neural Processing SDK from the Qualcomm Developer Network. There's a link there. It supports several different chips in the 800 series, 600 series, down to the 400 series. It also supports the Snapdragon 820AM platform, which is the automotive platform, and Snapdragon Flight, which is a drone platform. It uses for Android the Android compilers supporting GCC and Clang, and then for Linux it has support for ARMv7, ARMv7 hard float, ARch64, and we'll also run on x86 64 workstations, but that's mainly just for testing and development purposes. It's not a fully optimized runtime. The developer tools, we have SnappyNet Run, which is a way to quickly run a network that's been converted into a DLC. And we have the various converters that will take the native model formats, do some model optimization, and then turn them into the deep learning containers. We have Snappy Diag View for reviewing the diag logs that are generated while the models are being run. DLC Info, which will print out a text form of all the different layers, so you can analyze what the inputs are, what the output layers are, basically get a sense of the overall model. Snappy DLC Quantize, which will take a series of inputs and be able to generate the quantization parameters for the outputs that can be used to run for the DSP. Snappy Bench, which can give you the inference times per layer and some other metrics when you're analyzing your networks and testing for regressions and performance. And then recently, there's been a couple other additions. One is the Onyx converter that can convert Onyx models to DLC. And then a DLC viewer, which will allow you to do a nice analysis of models inside your browser. And you can go and do a deep dive through the various connections of the model. So the general workflow is you get a model in the native format. You would run it through the conversion tool, for instance, like the Onyx converter. You get the DLC model file, and then you can run that on the Snappy runtime. If you're doing some prototyping, there's also a facility called the user-defined layer, where you can add in your own layer into the model that's not a supported operation, for instance, and then make that be part of the runtime. So you see there's the various models are supported. There's a list of a subset of some of those models there for GoogleNet, Inception, AlexNet, ResNet, et cetera. So models can be, DLCs can be quantized or non-quantized. The quantized models run on the DSP directly. If you have a non-quantized model, it can also run on the DLC, on the DSP. It will auto-quantize in that case. If you have a quantized model, it can be dequantized and then run in 32-bit float mode on the CPU or GPU. It just depends what you have. So it can do either, but you won't go through that quantization or dequantization phase. So knowing which backend you're targeting may save you that step if you do it beforehand. So for NN API support, clearly TensorFlow Lite supports the NN API backend. You can also use other frameworks that can then feed into NN API. What we do is implement the Android NN HAL that has the DSP runtime, the OpenCL runtime, targeting the DSP and the GPU. And then the CPU is obviously provided by Google as part of the framework. So these are the sets of operations spec'd out for NN API. The ones in green there with the 1 are the ones that are currently supported. There's a bunch of other ones that we feel are missing actually from the spec for NN API that we think are really important, and there's some of the priorities that we listed with those as well. All right, so Hexagon NN is the open source library that supports machine learning operations on the DSP. They're currently already used by some other runtimes other than just Snappy, or Snapdragon Neural Processing Engine, or the or Android NN. Mace has taken the code and forked a version of it. It's part of their, Xiaomi has done that in the context of Mace, which they released this year. And then TensorFlow has a contrib library, which I believe the Hexagon team has been working with to provide an optimized backend for running TensorFlow. So some of the caveats of using Hexagon NN are that you have to have a test signature to run binaries on the DSP. There is tools to do the signing, but you will typically either need an OEM signature or you will have to have a test signature. And if you're going to run a test signature, you usually need a device that you can have rooted. So if you're trying to do this on a commercial device, you'd want to have a device that you can buy and then root in order to do your testing. So the flow for the signed binaries is you have the libNN from Hexagon NN. You have tools that can get the device serial number. You run it through the ELF signer. It generates this test signature and a version of the library which works with that. Those both get pushed to the device, and when those things are both present and supported, then you can basically run your program on the DSP. So here's the feature matrix. So there's several different versions of DSPs, and then there are several variants of the DSP. So there's audio DSP, compute DSP, sensors DSP, a sensor core DSP, and then the mobile DSP. So the mobile DSP is, or modem DSP, I guess. So the modem DSP clearly runs the modem most of the times, but there are configurations where you have a device like a tablet that may not have a modem. The processor may have a modem DSP, and then it can also be used for compute. So that's the last column there for the MDSP. QWERT is the operating system that runs on the DSP, and then LA is Linux Android. So there's Android variants supported on the application processor. And in the case of 820, there's the automotive variant, which is not running Android. It's running a Linux, standard Linux, in fact, AGL variant. So HVX is supported on the V60, V62, and V65 Hexagon DSPs. I had mentioned earlier that Snapdragon Flight was supported. It actually has an older DSP that does not support HVX, so the framework will not support the DSP on that particular platform. let's see. I think, and all this stuff is inside the release notes for the Hexagon SDK. All right. So some time for the end. So in general, we see the opportunity to take all these mobile-centric technologies and all the innovation that's going on in the mobile space, and then taking that and applying it to other markets like automotive, healthcare, et cetera. And we really see that it's exciting to see all the different things being enabled by AI today. All right, thank you.
Thank you, Mark. Any questions? Any question for Mark?
Thanks a lot. Do you plan any collaboration with the ARM NN so that you use maybe a compute library or that you contribute some part for your GPUs or the DSP?
Yeah, we've been exploring with them what the collaboration opportunities are. Certainly, if you look at the Hexagon NN, once there's the plug-in interface defined for ARM NN and it's solid, then there's an opportunity for us to potentially create a plugin using the Hexagon NN APIs to let the GPU be used. We would have to create a separate plugin for the Adreno GPU because, as he mentioned, there could be an order of magnitude difference in performance for the Mali GPU kernels that are there right now. But yeah, it does seem like an interesting prospect, and definitely we want to pursue what opportunities there might be there for collaboration.
Okay, thank you very much.
Great, thank you.
I think we can have a 5-minute break, and at the hour we start with Tom Lane from Amazon.